Hi everyone, welcome back to my channel. And today we'll dive into the transformer architecture. And I walk you through it by using its landmark paper, Attention is All You Need, where it was first introduced. I'll break it down step by step so it's easy to grasp and a bit more fun. So let's jump in. Let's start with the big picture. Where does the transformer fit in the AI field? At the top level, we have artificial intelligence. Inside AI, we have machine learning, where the systems learn patterns from data. And inside machine learning, we have deep learning, which uses large neural networks to automatically learn representations. And right at the center of deep learning is transformer architecture. So the main idea is that the transformer has become fundamental model architecture which could be reused in different kinds of problems. Something like multimodal, which combine text, images, videos. The example could be Gemini and Sora. For NLP, natural language processing, we deal with the human language like ChatGPT and BRT. And then we have science, which is for the task like AlphaFold. And then there's computer vision, the VIT for images. Finally, there's audio, something like whisper for speech. So key takeaway is that transformer has become a unified architecture for almost all modalities like text, audio, images, and more. And we are moving from model per task to one model for all. Seeing the big picture, the next question is, why do we even need a new architecture? What was wrong with the older approaches? This slide summarizes the two big pain points people had with RNNs and CNNs, especially when we deal with sequence like text. Let's start with RNNs. The core issue is computation is sequential. In RNN, the hidden state at time t, which we call ht, depends on the hidden state from the previous state, ht-1. This sounds reasonable, but it has a big consequence. You don't really parallelize the work inside a single chaining example. If a sentence has 100 tokens, you basically have to process token 1 first, then token 2, then token 3, one by one, and they make chaining slow and hard to scale on GPUs. You also see a complexity note here. The cost per layer is often written as O n times d squared, where n is a sequence learns, and d is the hidden dimension. You don't need to memorize this expression, just remember the idea. Longer sequences and bigger hidden size get expensive fast. Now the second problem is long-range dependencies, meaning how well can the model connect information from far apart positions in a sequence. For RNNs, the path between two positions is basically the number of steps between them. So the path learned is O n. If two important words are far apart, the information has to travel through many steps, and it becomes harder for the model to learn the dependency reliable. CNNs are different. CNNs can be more parallel-friendly, but they mainly capture local patterns at each layer. If you want a token to see the full context, you often need to stack many layers so the receptive field grows. That's why the slide says CNN may need many staking many layers, something like O log kn, to cover the entire sequence. Again, the exact formula isn't the main point. The intuition is CNNs need depth to connect faraway positions. So what's the goal? Ideally, we want two things at the same time. We want computation that is easy to parallelize, meaning only on O1 sequential operations, so we can process many tokens at once. And we also want the path length between any two positions to be constant, O1, so any token can directly interact with any other token, even if they are far apart. And that's exactly what transformer is designed to achieve. In the next part, we'll see how it does that. Alright, now let's zoom in and look at the transformer at a higher level. This slide is basically the classic diagram from attention is all you need, and the key idea is the transformer is an encoder-decoder model. On the left, we have encoder. You can think of encoder as a machine that reads input sequence like a sentence and converts it into a set of rich representations. The slide says it's a stack of n equals 6 identical layers. It just means we repeat the same type of blocks 6 times. The encoder takes input x and maps it into a continuous representation z. In simpler words, it turns raw tokens into vectors that capture meaning and context. On the right, we have decoder. It's just a stack of n equals 6 identical layers, but its job is different. It generates the output sequence. The important detail here is that it generates output one element at a time, which is what autoregressive. So at each step, the decoder looks at what it has generated so far and then predicts the next token. Now let's follow the diagram from bottom to top. At the bottom, both sides start with embedding. We don't feed words directly into the model. We first turn token into vectors using an embedding layer, and right after that, we add positional encoding. That's because the transformer doesn't process tokens step by step like an RNN, so we need to explicitly give it information about token order, like which token is first, second, third, and so on. Inside each encoder layer, the two main blocks you see are multi-head attention and a feed-forward network. Attention lets each token look at other tokens and decide what matters. The feed-forward network then transforms the presentation at each position to make it more expressive. And you will notice 8 none around them. There is the residual connection plus normalization, which helps chaining stay stable when you stack many layers. On the decoder side, it's similar, but with an actual twist. The first attention block is mask, multi-head attention. Mask means the decoder is not allowed to pick at future tokens, so when it's predicting the next word, it only uses words it has already generated. Then the decoder also has another attention block that connects to encoder output. This is how the decoder can attend to the input while generating the output. Finally, at the top, we convert the decoder's final hidden vectors into actual predictions. That's the linear layers and softmax, which produce output probabilities over the vocabulary. So if you remember just one sentence from this slide, the encoder builds context-rich representations of input, and the decoder uses attention to generate output step by step with embeddings, position encoding, multi-head attention, and feed-forward layers as the core. Now let's move on to the core engine. Scale dot product attention. If you understand this slide, you basically understand what attention is doing under the hood. The first thing to know is that the input to attention is 3 sets of vectors, queries, keys, and values, usually written as Q, K, and V. You can think of it like this. For each token, the model asks a question: what information do I need? That's the query. Every token also provides a kind of label. They describes what it contains, that's the key, and the actual content we want to pass along is the value. Now look at the formula here. It looks scary at first, but it's really just a simple pipeline, and the diagram here shows it step by step. First, we take Q and K and do a dot product, QK transpose. That gives us similarity scores. In plain word, it tells us for a given token how much should it pay attention to every other token. Next, we scale those scores by dividing by the root of decay. Here, decay is the dimension of the key vectors. The intuition is that when the dimension is large, the dot products can become large in magnitude, and they can make the softmax too sharp. When softmax get too sharp, gradients can get tiny and chaining becomes unstable. So this scaling keep the number in a healthy range. Then sometimes we apply a mask, which is optional depending on the situation. The most common case is in the decoder. We mask out future positions so the model can't cheat by looking ahead. After that, we apply a softmax. Softmax turns those raw scores into probabilities so that for each query, all the attention weights add up to 1. Now we have a clean distribution that says how to spread attention across tokens. Finally, we take a weighted sum of the values V. And that's the last mathmal block in the diagram. And this is the actual output of attention. Each token gets a new vector that is a mixture of other tokens' value vectors weighted by how relevant they are. So the one sentence summary is: attention computes relevant scores between tokens, normalize them into weights, and use these weights to combine information from the value vectors. And once you have this, multi-head attention is basically the same idea repeated multiple times in parallel with different projections. The next question is, why do we use multi-head attention instead of just one single attention mechanisms? The idea is that having multiple heads and let the model look at the data from different angles at the same time. For example, one attention head might focus on the immediate neighboring words to understand local context, while another head might focus on finding words that are far apart in a sentence but are related in meaning. A third head might pick up on certain grammatical structures and so on. So by having multiple heads, the transformer can capture different types of relationships all at once. Instead of just having one view of the sequence, you get multiple views that are learned in parallel. That's why on the slide, And it says we project QKV linearly multiple times, like 8 times, so each head can focus on a different representation subspace. In simple terms, each head is like a different lens that the model uses to understand data better. Then we just concatenate all these different heads together and run them through one more linear layer to mix them back into a single output. So the takeaway is that multi-head attention lets the model attend to different aspects of the data at the same time, making it much more powerful and flexible. Now let's look at 3 different ways attention is used in the transformer. First, we have encoder self-attention. In this case, the queries, keys, and values all come from the encoder's previous layer. That means each position in the encoder can attend to every other position. There is no restriction. Each token in the input can look at the whole input sequence. Next, we have the decoder mask self-attention. Here, the queries, keys, and values all come from the decoder itself, but we apply masking. That means each position in a decoder can only attend to itself and the position before it. It can't look ahead at future tokens. We do this by setting future positions to negative infinity before the softmax, so it can't pay attention to them. Finally, we have encoder-decoder attention, also known as cross attention. In this case, the queries come from the decoder, so from the part that's generating the output, but the keys and values come from the encoder's output. This lets the decoder look up information from the encoder side and figure out what they need from the original input. So those are 3 ways attention is used: encoder self-attention, decoder mask self-attention, and encoder-decoder cross attention. Alright, so we've covered attention, which is a part that makes information across different positions. Now let's look at other major piece inside each transformer layer, which is a position-wise feed-forward network. This is basically the processing unit that happens after attention, and the key idea is that it's applied to each position separately and identically. So every token goes through the same little neural network with the same weights. The tokens don't talk to each other inside this part. Any interaction across tokens already happen in the attention step. On the slide, you can see the formula. It's a very simple 2-layer network. First is a linear transformation, then a ReLU nonlinearity, and then another linear transformation. In notation, it looks like ffnx equals mix of 0 and xw1 plus b1, and then we multiply by w2 plus b2. And what's also important is the dimension expansion. In the original transformation setting shown here, the model dimension is 512, but inside the feed-forward network, it is expanded to 2048, and then it projects back down to 512. So you can think of it as taking the representation blowing up to a larger space to do richer processing, and then compressing it back to the model size. A nice way to build intuition is the analogy at the bottom. It's similar to 1-by-1 convolution in CNNs. It makes information across feature channels at each position, but it doesn't mix across positions. So the takeaway is simple. Attention is the part that connects tokens, and the position-wise feed-forward network is the part that transforms each token's representation in a deeper, nonlinear way. So we've seen attention and the feedback network. Now there's one more essential ingredient in the original transformer: positional encoding. The problem is simple. Unlike RNNs, the transformer has no recurrence. It doesn't process tokens one by one in time order. So by default, the model doesn't automatically know which word is first, which is second, and which is last. In other words, without actual help, the transformer has no built-in sense of order. So what we do, we inject order information directly into input. That's what position encoding is for. We create a position vector for each position in the sequence, and we add it to the token embedding. And I want to emphasize the point on the slide. We sum them, we do not concatenate them. So the embedding dimensions stay the same, but now each token representation carries both content information and position information. In the original paper, they use sine and cosine function with different frequencies to build this position encoding. That's what these two equations are shown. For even dimensions, they use sine function, and for all dimensions, they use a cosine function. The position is the posturn. And the frequency changes across dimensions using this factor. You don't have to memorize the equation. The main idea is that each dimension has a different wavelength, so together they create a unique smooth signature for every position. Now, why sine and cosine? First, they make it easy for model to reason about relative position. The key trick is that when you shift the position from pose to pose plus some offset, the new sine and cosine value can be written as a simple combination of the old ones. So the model can learn how far apart the two tokens are used, basic linear operation inside attention, instead of needing a spatial mechanism just to compute distance. Second, sine and cosine are generated by a formula, not stored as a learned table for a fixed set of positions. That means you can extend them to positions the model didn't explicitly see during training. And the pattern still behaves consistently, so in practice this helps the transformer handle sequences that are longer than the training samples. So takeaway is sine and cosine gives every position a stable signature, and they also make relative distance information easier to use, while still generalizing to longer lengths. Alright, in this slide, I want to highlight one practical design choice in the original transformer that improves engineering efficiency. And embeddings and weight sharing. First, embeddings. We start with tokens, which are just discrete IDs, and we need to convert them into continuous vectors. That's what the embedding layer does. It learns a vector representation for each token, and the size of that vector is the model dimension, which we call the model. Now, the key point on this slide is weight sharing. And instead of using completely separate matrices everywhere, the transformer can share the same weight metric across three places. One, the encoder input embedding, two, the decoder input embedding, and three, the final linear layer right before softmax, which maps the hidden states back to vocabulary logics. So in other words, the same matrix can turn token IDs into embeddings, can also be reused at the output side to turn hidden vectors into vocabulary scores. This reduces the total number of parameters and makes the model more efficient. Finally, there is a small but important detail in the bottom. The embeddings are often scaled by the root of the model. The idea is simply to keep the magnitude of the embeddings in a good range so they match the scale of the other signals in the network, especially when you add positional encodings and pass everything through attention and feed-forward layers. So takeaway is embeddings turn tokens into vectors, and weight sharing ties the input embeddings and output projection together to save parameters and keep the representation space consistent. Alright, so let's wrap everything up with a simple question: why did the transformer win? Why did it replace so many older architectures so quickly? This slide is a recap of comparison table from the paper. It compares 3 families of layers: self-attention, recurrent layers, and convolutional layers, using 3 criteria: complex computational cost, how many operations must be done sequentially, and the path length between 2 positions. For self-attention, the complexity is written as O(n squared d). So yes, it grows with the square of sequence length, but look at the other 2 columns. The number of sequential operation is O1 and the path length is also O1. That's a key advantage. Even though the computation can be heavy, it's highly parallelizable, and any token can directly connect to any other token in a single step. For recurrent models, the complexity is O(n d squared, but the big drawback is that the sequential operations are O(n). You can't fully parallelize across time steps because each step depends on the previous one. The path length is also O(n), which makes long-range dependencies harder to learn. For convolutional models, the sequential operation can be O(1), which is good for parallelism. But the path length grows like O log n, so to connect faraway positions, you still need multiple layers. So the table is basically telling us transformers hit a sweet spot. They are parallel friendly like CNNs, but they also give direct global connection like an idealized shortcut across the sequence. They lead to the 3 practical reasons listed below. First, parallelism. Transformers chain faster on GPUs because attention can be computed parallel across all positions. Second, long-range dependencies. Self-attention creates direct connection between all words, so the model can relay distance tokens without information having to travel step by step through many layers or time steps. Third, interpretability. Attention heights give us a way to visualize what the model is focused on, which sometimes help us understand relationship inside the input. So the main story of why transformers become dominate: they scale well with smaller hardware, and they handle long contacts more naturally, and they provide a clean, flexible building block. They work across many tasks. And with that, we've reached at the end of the transformer overview. Based on attention is all you need. If this video helped you, please like, subscribe, and leave a comment.